वाली में है उनको उनकी भाषा में उत्तर देने का हम प्रयास करेंगे। तो चलते हैं, शुरुआत करते हैं। मैं अपना स्क्रीन शेयर करता हूं। जेम्स वेब स्पेस टेलीस्कोप के बारे में ये खास क्वेश्चन एंड आंसर सेशन है। हम सब लोग यहाँ पर जो आज हैं वी आर एस्ट्रोनॉमर्स working at the National Center for Radio Astrophysics, which is part of the Tata Institute of Fundamental Research, which is located in Pune, in Maharashtra state of India. Space telescope के बारे में today my team consists of 4 people. We have Anirban Chakraborty, we have Rashi Jain, we have Yash Bhusare, who are all 3 of them are PhD students at our institute, and they are all doing their PhD, their doctoral thesis degree in different areas of astrophysics. I am myself Yogesh Vardekar. I'm a professor here at NCRA, and I do my research in areas of galaxy evolution. The James Webb Space Telescope is named after a gentleman named James Webb, who used to be the astronomer, who used to be the administrator of NASA during the time when NASA had the Apollo program in the 1960s. And as all of you know, in 1969, around this time of the year, the first man, Neil Armstrong, set foot on the moon. And Mr. Webb was the NASA administrator through much of the 1960s. That's why this new telescope is named after him. It's an international collaboration, which of course involves NASA. But in addition to NASA, it involves the European Space Agency, which was used to launch the telescope into space. There were a number of NASA centers which were involved, and the whole effort was managed by the Goddard Space Flight Center in Maryland, in the United States. They had a number of industrial partners. Their largest industrial partner was a company called Northrop Grumman. And after the launch of the telescope, the responsibility for operating the telescope has been given to the Space Telescope Science Institute, which is located in Baltimore in Maryland, and which also presently runs and operates the Hubble Space Telescope. It's a very large effort involving thousands of people in different continents. This is a picture of maybe 100 of them who had gathered together for a meeting at the Goddard Space Flight Center in Maryland, where they have constructed a life-size replica of the telescope, which you see in the background. That's a replica of the James Webb Telescope. The thing to remember is that the James Webb is an infrared telescope. What does that mean? It means that it observes the sky at wavelengths that are longer than the light that we can see. Another thing to remember is that the primary mirror of the James Webb Space Telescope consists of 18 different segments, and which have together a diameter of about 6.5 meters. This is much larger than the mirror of the Hubble Space Telescope, which has a primary mirror of 2.4 meters in diameter. So here's a comparison of the overall size of the Hubble Observatory and the James Webb Observatory. Hubble is like a big truck, okay? A rather large truck, or like a Volvo bus, if you're familiar with that. Webb is, on the other hand, the size of a small plane, like a Boeing 737 plane, which we can see commonly across India. So it's clearly much bigger than the Hubble Space Telescope, but that is what makes it really interesting. This is the overall layout of the telescope. There is the mirrors that you see, which are colored gold over here, and they're colored gold because they're plated with a reflective coating of gold. Gold is a very excellent reflector of light, particularly of infrared light. So that was chosen to coat the beryllium mirrors of the James Webb Space Telescope. So what you see at the center is the primary mirror. The light falls on the primary mirror and gets reflected towards the right to the place called the OTE secondary mirror. And then it gets reflected again, and it goes through a hole at the center of the primary mirror to the back side of the primary mirror, where there is the instrumentation module. The telescope is kept extremely cold. And the way to keep it cold is to keep it perpetually pointed away from the sun and protected by this large sun shield, which you can see in light blue color at the bottom. This sun shield is the size of a tennis court, and it ensures that no sunlight ever falls directly onto the main mirror or onto the secondary mirror of the telescope. On the other side of the sun shield is the spacecraft bus, and also on that side is a radio dish which allows the telescope to communicate with Earth. By placing it very far away from Earth at a special location, which we shall see in a minute, the telescope can be kept extremely cold at a temperature of around 40 Kelvin. That means about more than minus 230 degrees Celsius. So as I said a little minute ago, Webb observes in infrared light. So the visible light are the colors of the spectrum that we are all familiar with, going from violet all the way to red. Infrared are longer wavelengths or lower frequencies compared to visible light. The infrared itself is divided into near infrared, mid infrared, and far infrared bands. And the infrared sensitivity of Webb's instruments allows us to observe a little bit of the visible light spectrum, the entire near infrared part of the spectrum, and the entire mid infrared part of the spectrum. Beyond that, you still have a part of the infrared, which is called the far infrared. This is a part of the spectrum which is not observable with the James Webb Telescope. There are only 4 instruments on board the Webb. NIRSPEC is a spectrograph, NIRCam is an imaging camera. They operate from 0.6 to 5 microns. Then there is the fine guidance sensor, FGS, and the near infrared imager and slitless spectrograph, which also operates in the near infrared band. If you go and observe in the if you want to observe in the mid infrared, then you have to go and observe with the MIRI instrument, which observes all the way from 5 microns to 28 microns. And it does both imaging and spectroscopy. So why is this important? Because in the visible, is the light we can see emission from stars like the sun and so on. But if you go to cooler stars, which are much more abundant than stars like the sun, these cooler red stars emit most of their light in the near infrared. And in the near infrared, dust begins to become transparent. We are able to see through dusty environments. In the mid infrared, things like planets, comets, asteroids, as well as dust warmed by starlight and protoplanetary disks begin to shine bright. And therefore, in order to study these objects, the mid-infrared band is very, very useful. Webb was designed to study the universe and to handle 4 major areas of research in astrophysics. The first is to ask the question, when did the first stars form? And can we image and see those stars directly? So this is called first light. We'll come to that in a minute. And the epoch of reionization. That was the first science theme of Webb. The second science theme involved the assembly of galaxies. How did galaxies form? When did they form their stars? Were these stars, under what conditions were these stars formed? At what rate were these stars formed? And how did galaxies merge together and form larger galaxies to make the universe as we see today? Within galaxies, the birth of stars and protoplanetary systems is a very important one. And in our own galaxy, the Milky Way, we are able to study the evolution of the birth of stars and the evolution of stars in their early life and their development of protoplanetary systems very, very effectively because using Webb, because of that feature that I described earlier, that at mid-infrared wavelengths, one is able to peer through the dust and see what is going on behind the cloud of dust, which we couldn't do earlier. Formation of planets, origins of life, obviously are very interesting. And as we shall see today, all the images that have been released last week by the Webb cover all of these 4 different themes. It was launched on Christmas Day in 2021 at 5:30 in the evening from the Arianespace's site, launch complex in South America. And what you see here right on top is where the telescope was all folded up and put inside. And the reason it had to be folded up was that this was such a big telescope, it could not fit inside the rocket unless it was folded up in many different ways. But this, of course, meant that this folded up telescope, which is there, that folded up telescope is now at great risk because there are a lot of factors, things that can go wrong when it is opening up. So there were more than a few hundred critical steps in the commissioning of the observatory. Where is this observatory placed? It is placed at the Lagrange L2 point, which is shown towards the right over here. The advantage of putting it any telescope there is that, first of all, the Earth and the Sun are always in one direction with respect to the telescope. So you can position the sun shields in such a way that they are always keeping the telescope in shadow. And perhaps more importantly, at that L2 point, the telescope gets dragged along with the rotating frame of the Earth going around the sun, so that it always remains in a straight line between the sun, the Earth, and the Lagrange L2 point where the telescope is located. So how far away is this site? It is about 15 lakh kilometers away. For context, the distance to the moon is about 4 lakh kilometers. So it is nearly 4 times further away than the moon. So let me give you a quick outline of what all happens since the Big Bang, because many of the questions that we will handle today will need this as context. So the universe formed 13.7 billion years ago in a massive explosion, which is known as the Big Bang. Within the first fraction of a second, there was a very rapid expansion of the universe, which is known as inflation, where the size of the universe increased by many, many orders of magnitude. About 4 lakh years after the Big Bang, the universe had cooled enough, expanded enough, cooled enough for the ions, the protons and electrons to come together and form hydrogen atoms. and that is known as the last scattering surface. It's also the epoch from which we observe the light known as the cosmic microwave background. After that, nothing much happened. This is known as the Dark Ages. During this time, hydrogen, under its own gravity, hydrogen atoms began to be drawn towards each other. They formed hydrogen molecules, and eventually a sufficiently high density was reached for star formation to begin. Now, exactly when these first stars formed, we don't know. The the JWST is going to definitively answer that question, because it is going to help us find, directly image, detect the first stars. Indications seem to be from the first results from JWST is that the first stars formed not about 400 million years ago, 400 million years after the Big Bang as indicated here, but possibly 300 million years after the Big Bang or even earlier. After that, the stars began to come together and form galaxies, and the galaxies began to evolve by themselves. Galaxies merged with each other to form larger galaxies and so on, until we reached the universe of today. So today we are going to try and look at questions dealing with the most distant galaxies, the first stars and so on, as well as the evolution of galaxies, which is of course connected to the evolution of stars, which of course will be connected to the evolution of planetary systems and the possibility of life. Okay, so now we begin with the first set of questions with this broad background. The first question that has been asked by Ashutosh from Rajasthan, if JWST can see 13.5 billion years back, is it possible to make a telescope that can see further than the beginning of time? Okay, so I think one way of looking at this question is, how far can JWST see? Okay, so JWST can see approximately 13.5 billion years back. That is correct. It cannot see anything after that, because after that there is just neutral hydrogen in the universe, which is not emitting any light at the infrared wavelengths that JWST can observe. So it can't see further than that. And of course, nothing can see further than the beginning of time, because the universe didn't exist before the beginning of time, which means before the Big Bang. The next question is, I know JWST works in infrared range. Is it possible for JWST to capture the first light? Yes. So the answer to that is yes, so that we can have a clear image or something new explanation for the moments after the Big Bang. So I must tell you that yes, we will capture the first light with JWST, but it is not moments after the Big Bang. It is quite a long time after the Big Bang. So the Big Bang happened, as I said, 13.7 billion years ago. That means 13,700 million years ago. But what we will be able to see the first stars, again, we don't know when, how far back that will go. But I think it could go as far back as 100 or 200 million years after the Big Bang. Okay, so it's still not moments, but about, say, a few 100 million years after the Big Bang is what we will be able to probe. So now I will hand over to my colleagues to start dealing with additional questions. One second. Yeah, Rashi, I think you're next. Is she on?
Yeah.
Yeah.
So I'll share my screen.
Yeah. Please share your screen.
Okay. So can you see my screen?
Yes, we can see your screen. Yeah, you just you may want to just put it in full screen mode or slideshow
Yeah.
mode. No, you just click on view and slideshow.
Yeah, I'll do that. Wait. So,
yeah, you're good. I think you can start.
yeah. So at first I'll answer the question by Amit. He has asked the questions in Hindi. So he has asked like है ये दूरदर्शी कहाँ पर स्थित है? तो जैसे कि योगेश ने अभी बताया था कि यह दूरदर्शी एक्चुअली वेट यहाँ पर L2 पॉइंट पर स्थित है, जो कि पृथ्वी से 15 मिलियन किलोमीटर दूर है। और उसके अलावा आपने ये पूछा है कि I'll just share it like this only. So अंतरिक्ष में दूरदर्शी कैसे स्थापित की जाती है? तो यह दूरदर्शी wait. यह दूरदर्शी ईएसए के एरियन रॉकेट के द्वारा स्थापित की गई है। इन्होंने यह भी क्वेश्चन पूछा है कि इस टेलीस्कोप के उद्देश्य क्या क्या हैं। तो इसमें सबसे बड़ा मेन उद्देश्य है कि ये हमारे सौर मंडल के बाहर जो ग्रह एग्जिस्ट करते हैं, जिनको एक्स्ट्रा सोलर प्लैनेट्स कहते हैं, आज तक हम उनका बस नंबर ही जान पाते थे ढंग से, बट अब JWST के सहायता से हम उनके स्पेक्ट्रम को सीधे सीधे देख के बता सकते हैं कि उनके वायुमंडल में कौन से एलिमेंट्स एग्जिस्ट करते हैं। और इसके अलावा ये ब्रह्मांड के सबसे पहले बने हुए स्टार्स को भी देखने वाला है, और यहाँ तक कि यह ब्रह्मांड की सबसे पुरानी आकाश गंगाओं को भी देखेगा, जो सबसे ज्यादा दूरी पर स्थित है। इसका रीजन ये है कि हबल स्पेस टेलीस्कोप हमारा वो हबल स्पेस टेलीस्कोप ऑप्टिकल में देखता था, जो विजिबल लाइट होती है, और वो लाइट रेड शिफ्ट होकर इस हमारे पास पहुंचती हुए इंफ्रारेड में पहुंच जाती है। तो JWST इंफ्रारेड में देख सकता है, इसीलिए और ज्यादा दूर की गैलेक्सीज को देख सकता है, जो लाइट एक्चुअली में ऑप्टिकल में इमिट हुई थी, लेकिन आज हम उसको इंफ्रारेड में देख रहे हैं। इसके अलावा यह भी पता चला आएगा कि आकाश गंगाओं ब्रह्मांड की उत्पत्ति कैसे हुई थी, क्योंकि ये बहुत दूर की आकाश गंगाओं को देख सकता है, और हमारे पास अभी पास की आकाश गंगाओं की भी का ज्ञान भी है, तो हम पता कर सकते हैं कि ये आकाश गंगाएं समय के साथ कैसे इवॉल्व हुई हैं। इन्होंने एक क्वेश्चन ये भी पूछा है, क्या अंतरिक्ष में मुक्त अवस्था में पाए जाने वाले आकाशीय पिंड इस दूरदर्शी से टकराकर इसको नष्ट नहीं कर देते? तो एक्चुअली यह एस्टेरॉइड बेल्ट से काफी दूर है, लेकिन माइक्रो एस्टेरॉइड्स इसको हिट कर सकते हैं, जिससे इसको इतना नुकसान नहीं होने वाला है। इन्होंने ये भी पूछा है कि भारतीय खगोल विज्ञान को इससे क्या लाभ होने वाला है। तो मैं ये बात कहना चाहूंगी कि भारतीय वैज्ञानिकों को भी इसके डेटा का एक्सेस मिलेगा, जिससे कि इसके डेटा का हम उपयोग कर सके, और यूएस में भी कई भारतीय मूल के वैज्ञानिक इस JWST की टीम में कार्यरत हैं। अब इसके बाद now I have got some questions regarding SMAX 0723, and the questions are about the gravitational lensing that is present in this image. So I'll talk about what this SMAX 07723 is. So it is a galaxy cluster which is located at 4.6 billion light years away from the Earth, and it has captured many galaxies, and some of the galaxies have not been captured before by any of the telescopes. And you can see that these some galaxies are distorted. So like this is happening because of the gravitational lensing. Okay, so now the Suresh from Gujarat has asked this question. Like, can you please explain the gravitational lensing that is being observed in the image, and can you also please describe what the gravitational lensing is and how is it beneficial? So gravitational lensing is basically the bending of the light because of the massive objects. They distort the light because of their gravity, and because of the distortion of the light, we actually get to see some of the photons that could not reach us otherwise. So we can get to see a lot of light as compared to the case in which the light is not bent. Also, this gravitational lensing depends only on the mass of the object, which is warping the space-time. So if we can account for this gravitational lensing, we can get to know that how much mass is exactly present in the galaxy cluster. Because if we look at the galaxy cluster, uh, we can see only the ordinary matter, only the baryonic mass, by just looking. But because of the gravitational lensing, we can actually get to know about the other mass that is present as in the form of the dark matter. Again, about this Max 0723, Parth from Maharashtra has asked questions. So his question is, we see that many needle-shaped galaxies are warped due to the gravitational lensing. So my question is very simple. Are these similar-looking galaxies actually images of just one galaxy that is behind an object that bends the light? Or is there much more bending and twisting by other objects in order to form multiple images of one galaxy? So basically, he wants to know that like the arcs that we are seeing in this image, are they the multiple images of one particular galaxy, or are they the different galaxies? So actually, both are the possibilities. So gravitational lensing has two types. One is strong lensing, and other is the weak lensing. So in strong lensing, the light distorts much more, and we can see structures like rings and multiple images of one object. And in weak lensing, only the shape of the galaxy gets stretched and distorted. So this is an image in the background which shows a gravitational lensing. You can see this ring-like structure which is formed because of the strong lensing. So now, how do we get to know whether these galaxies are the same, or are they the images? Whether these galaxies are the same, or are they different? So one thing that is particular to each galaxy is their spectra. So we can get the spectra of these galaxies through JWST, and we can match the spectra of the different galaxies. And if the spectra is same, then we can say that the galaxies are the same. But if the spectra is different, then we can say, okay, these galaxies are different galaxies. Now there are other questions about
Yeah,
Stephen's
Rashi,
quintet.
if I may interrupt, I think
Yeah,
we
yeah,
will
okay.
come to Stephan's quintet a bit later. Okay.
Okay, sure,
So
sure. I'll just stop sharing my screen
go,
then.
go in a certain order as we had decided. So you've
Okay,
jumped a little
sure.
ahead, but that's okay. We will handle that.
Yeah,
So
okay,
stop
sure, sure.
sharing your screen.
Yeah, I'll stop that. Yeah.
Yeah. So 1 second. Now
Mhm.
okay. So we have more questions, which also are very interesting, which set the context. So Shashikan B from Maharashtra is asking why galaxies have different color texture. What is its significance? And a related question comes from Mukesh Sahu from Odisha, who says the southern ring nebula image. Is it an exact image that is sent by the telescope, or is it an edited version? So I'll try to answer both of these questions together. If you want to take a color image of a bird, there is a starlight macaw which is shown in the picture. If you want to take a color image of the bird, what is usually done by your digital camera, whether it's on your phone or you have a dedicated digital camera, it takes images in 3 different filters: a red filter, a green filter, and a blue filter. And then you have some software which can combine these 3 images to give you the final color image. Naturally, if the bird is red in color, it will appear very bright in the red image, and it will be very faint in the blue image. The same is true of galaxies. When we observe galaxies, we don't observe them in color directly. We observe them in 3 different filters, the red filter, some green filter, and some blue filter. And then we, using a computer, we combine those images together to make it scientifically correct. Okay, so we combine the red filter, green filter, and blue filter. In the optical, we have a notion of what is the color of the bird. But if I ask you what is the infrared color of a bird or the infrared color of a galaxy, that makes little sense. But what is done there is analogous to what we do in the optical, is that we assign one infrared filter as the red filter. Usually we will pick the longest wavelength filter as the red filter. Something with a slightly shorter wavelength, we will pick as the green filter, and we will choose something with an even shorter wavelength as the blue filter. Then we will combine that, and then we will make an image. Is this image exactly untouched? No, that's not true. In order to make the image visually appealing, a lot of photoshopping is done on it. So there are experts at the Space Telescope Science Institute in Baltimore who just adjust everything so that the image looks visually as beautiful as possible. They also do, if there is some part of the image where there is an artifact or there is some damage to the data, they will also correct for that. So just like it's like called retouching in Photoshop. So they will do all of that and send you an image. So most definitely, in answer to Mukesh's question, this image is definitely an edited one. Another thing to remember, so now if a galaxy, I said that if a bird is red, it will be bright in red filter and faint in blue filter. Similarly for the galaxy. But if a galaxy looks red, which means it's bright in the red filter, what does that imply? It implies one of 2 things. One is that the galaxy has a lot of dust in it, which is absorbing all the blue light or the shorter wavelengths, and therefore the galaxy is looking red in color. Another reason why the galaxy may look red in color is because the universe expands as time goes on. Because of this continuous ongoing expansion of the universe, there is something known as Doppler shift, which shifts the entire spectrum of the galaxy towards longer wavelengths. Astronomers refer to this as redshift. So if you observe a galaxy at very high redshift, that means that its spectrum is shifted quite a lot towards longer wavelengths, towards the red part of the spectrum. In the case of the optical, but in the infrared, just think of it as something that increases the wavelength of light quite considerably. So a galaxy is red may indicate that A, it's very dusty, or B, it's very distant. And as you know, the James Webb is designed to find the most distant galaxies. So as newer and newer images appear of these distant galaxies, you will find invariably in the pictures that you will see, these galaxies will appear red in color because they're very faint at shorter wavelengths and they're only bright at the longest wavelengths that the Webb can observe. So this is, with this we come sort of to the end of this section on how the JWST operates and so on. Now we are going to move on to the next sections where my younger colleagues will answer most of the questions, which will be focused on specific images that were released last week. A few of the questions have been already answered by Rashi, and now we are going to move on to some other questions. So Rashi's already answered the question about SMACs, and so now we move on to some discussion on by Yash, I think, who's going to talk about the JWST image for SPACs and talk about diffraction spikes and so on. So over to you.
Yeah.
Rashi, you need to. I'll stop sharing, and Rashi, you
Yeah,
need
okay.
to share your slides.
I shared it.
Yeah. Hi. So
Yes, you're muted, huh?
yeah. Now I guess I'm fine. Nirvan, can you?
Yash, please continue. We can hear you, but I think it may still be a problem on the. Okay. So since Yash is not audible, let me try to take over. I hope that I am going to be audible. Trusting that I'm audible, I'm going to explain what's happening here. So this is an image of an exoplanet transit. So what is happening is there is a star, and in front of the star, one of the planets of that star is passing. This can be seen from Earth with a small telescope whenever there is a transit of the planet Mercury or of the planet Venus. These are very rare transits, but they can be observed, they can be seen. So what will happen when the transit happens is that the brightness of the star will decrease. So what is shown in the graph below is a light curve. So by 1 or 2%, the brightness of the star will decrease. And so this is known as an exoplanet transit, which is shown in this figure. Rashi, can we move to the next slide, please? And this is exactly what was seen for a very distant planet called WASP 96b. The starlight was coming in, and whenever the planet passed through, we saw a very great decrease in the flux from the not a very great decrease, a very small decrease in the flux that was coming from the planet, because it was that light was being from the star, because the light was being obstructed by the planet. And as you can see here, the 100 is 100% level, and it has gone down to about just below 99. Okay, so the decrease in starlight is just about 1%. Can we go to the next slide?
This is it.
Yeah, this is it. Okay. So this sets the context for the JWST transits. Now we will move on to and take the questions. Let me see if we can see the.
Yeah, so before we continue,
yeah,
there was one question related to exoplanets in Bengali from Ankita Sarkar.
Yeah.
So which I will answer now.
So please go ahead.
Yeah, so I'll first say the question in Bengali and then translate in English and give the answer in Bengali. So she is asking যে আমার প্রশ্ন হলো JWST এর বাকি ছবিগুলির মতন আমরা এক্সোপ্ল্যানেটের একটা ক্লিয়ার ছবি কেন পেলাম না, একটা স্পেকট্রোগ্রাফির ছবি কেন পেলাম? So her question is that why did we not get a direct image of the exoplanet from JWST as we did for all the other objects which have that have been released? So to answer Ankita's question, এই যে এক্সোপ্ল্যানেটের কথা আমরা বলছি, আদতে এইগুলো অনেক দূরে অবস্থিত হয়, এবং এই এক্সোপ্ল্যানেটগুলি যেই নক্ষত্রগুলিকে প্রদক্ষিণ করে তারা এই এক্সোপ্ল্যানেটের থেকে অনেক অনেক বেশি উজ্জ্বল হয়। তার ফলে যে কোনো মহাকাশ দূরবীক্ষণ যন্ত্রের মধ্যে দিয়ে আমরা যদি কোনো ছবি তুলি, তার মধ্যে এই এক্সোপ্ল্যানেটগুলোকে স্পষ্টভাবে এবং সূক্ষ্মভাবে তাদের দেখতে পাওয়ার সম্ভাবনা খুবই কম থাকে, এবং সেই জন্যই সরাসরি ইমেজ করা একটা এক্সোপ্ল্যানেটকে খুবই কঠিন। যদিও JWST-র উপরে একটি করোনাগ্রাফ বলে যন্ত্র আছে, যে যন্ত্রটি নক্ষত্র থেকে আসা উজ্জ্বল আলোকে আটকে দেবে এবং তারপরে দেখার চেষ্টা করবে আশেপাশের আলোগুলিকে, এবং JWST-র সেন্সিটিভিটি এতটাই হাই যে আমরা অপেক্ষায় থাকতেই পারি যে হয়তো আমরা একটা ডিরেক্ট ইমেজ পেতে পারি, বাট যদিও সেটা খুবই কঠিন পাওয়া। To answer her question in English, the thing is that the exoplanets are very far away, and they are often obscured by the bright light of the parent stars which they are orbiting. So taking pictures of these exoplanets the same way as we take pictures of planets, say like Jupiter or Venus in our solar system, isn't easy at all. The exoplanets are very dim, and they are practically invisible even to the powerful telescopes present today. Therefore, doing a direct imaging of distant exoplanets is very difficult. In a few cases, however, given that the JWST has a coronagraph instrument, so the coronagraph instrument is basically a device which will block the glare of the star, the parent star, and allow us to see whatever there is without the glare of the star. And this is very much the same technique that we use when we want to block the light of the sun during the day and look up things in the sky. So maybe, but it is very difficult in general to do direct imaging of exoplanets. So I hope that answers your question, Ankita, and we'll move ahead with the next questions.
Yes. So just a gentle reminder to the speakers, when you're speaking, please make sure your video is on, because if you're not showing any slides, then there is just a sort of black screen with names on the YouTube feed. So we move on now, and now we are ready to move on to the next object, and that is going to be the JWST image of Stephan's Quintet, which will be now introduced by Rashi, and she will answer one of the questions based on that. Go ahead, Rashi.
Hi, so I'm going to answer some of the questions on the Stephan's Quintet. So this is a galaxy group which is located in the constellation of Pegasus, and in one of the galaxies, NGC 7319, this one, it hosts a type 2 AGN. So I'll explain what this type 2 AGN is and what are the questions that we have got regarding this image. Okay, wait. Yeah, so wait. So this is the question that we have been asked by Manila Ramrakyani from Maharashtra. She has asked, how does NGC 7319 harbor AGN? So I think she wants to know how do we know that this is an AGN? And so first I'll give you a background. This is the image of this Stephan's Quintet taken by HST, and here we cannot just differentiate it from a regular galaxy. We cannot know whether this is an AGN or not. So, but while in the image taken by JWST, the core of the galaxy is very bright, and earlier we could not see this AGN because of the obscuring torus. So this is the structure of an AGN, in which there is, at the center is a supermassive black hole, and it is surrounded by this cylindrical structure, which is this is known as torus, and it is made of dust. But the mid-infrared observations can look through this dust, and this is why we can detect an AGN directly without the need of spectroscopy. So earlier the AGN could only be seen through spectroscopy, like we used to take the spectra and then determine whether it's an AGN or not. And also I want to point this out, this is a type 2 AGN which is present here. So it is because of its viewing angle, it is obscured by this torus, this structure. This is why we cannot see its emission directly, and this is why it's difficult to see it in optical, while from JWST it is easy to see it, because JWST sees it in mid-infrared, and it can actually look through this dusty torus. Yeah. So this is the question. This was my answer regarding this question. Thank you. I'll stop sharing.
Move on to the next object, which is I think the most beautiful image of the set, which is the image of the Carina Nebula. And we will have Anirban introducing this image and then answering some of the questions about it. Go ahead, Anirban.
Yeah, hello. You can hear me, right?
Yeah, Anirban, we can hear you. Please start.
Yeah, so we received a lot of questions regarding the two nebulae that JWST has captured, and a common thread on all of them were that a lot of people wanted to know about the nebula. And these questions are particularly asked by the following two people, Shati Devangan and Amit Tripathi. So what is a nebula? As you can see in this image, stars are born from giant clouds of gas and dust called these star-forming nebulas. And turbulence from deep within these clouds create high-density regions called knots. And these knots contain sufficient mass such that the gas and dust can begin to collapse from gravitational attraction. As it collapses, it begins to spin and material at the center begins to heat up, forming protostars. And eventually, the temperatures in the core reach so high enough that it is so hot and ignite nuclear fusion processes, and a star is born. So the nebulas are sites from where stars are born. And however, a star's mass is determined by the amount of matter that is available in these nebulas. And a star's life cycle, in turn, is then decided by its mass. So larger its mass and is the mass, shorter will its life cycle be. And throughout its life cycle, a star is facing a constant struggle between the force of gravity, which tries to collapse the star, whereas the star's core, which is fusing hydrogen and is very hot and tries to counteract this, is through gas pressure and setting up a condition of hydrostatic equilibrium in the star. A star is okay as long as it has this equilibrium between gravity pulling the star inwards and pressure pushing the star outwards. However, this does not continue all the way long, and there comes a time when the star runs out of the nuclear fuel at its center, and then it starts fusing higher and heavier elements, entering, say, a red giant phase. And however, the massive stars, as in the case of massive stars, as the final end to this process is when the nuclear fuel is entirely exhausted, is results in the blasting away of the star material into the space in the form of supernovae, as you can see on the right bottom of this diagram, while the core implodes into compact objects like neutron stars and black holes. However, for ordinary or less massive stars like our own sun, and they don't undergo such explosive events. Instead, their cores contract into tiny hot stars called white dwarfs, while the outer material simply drifts away, leading to what is known as a planetary nebula. So from this picture or this story, it is evident that the birth and the death of stars are intricately connected through nebulas, either planetary nebula in the case of low mass stars, or that is birth starting from star-forming nebulas. I hope this answers the general question regarding nebulas and how they fit into the general scheme of things regarding stars. Next, we will move on to the object of interest, the Carina Nebula. And a lot of questions were asked regarding this nebula by Dipanshu Shah, Anindita Sarkar, and A.S. Shahanshu. So this is on your screen, as you can see. This is the image of the Carina Nebula as captured by JWST. So the question that we received was, what are the some of the prominent things worth mentioning in this JWST image, given its superior clarity than Hubble? So this landscape of mountains and valleys that you can see speckled with some glittering stars all around is a nearby young star forming region called NGC 3324 in the Carina Nebula, some 7,500 light years away in the constellation of Carina. The nebula is home to countless young stars. It is essentially a stellar nursery. And these stars are so full of energy that they whip cosmic gas and dust around, shaping them into these peaks and valley-like structures that you can see at the nebula's edge. And this cave-like area that you see with which looks like a range of mountains on a moonlit evening is essentially the edge of a giant gaseous cavity inside NGC 3324 called the Cosmic Cliffs. And the tallest of the peaks in this image is typically about 7 to 8 light years high here. And this cavernous area has been carved from the nebula by the intense ultraviolet radiation and the stellar winds driven by extremely massive, hot and young stars located in the center of this bubble, just above the area shown in this image. The high energy radiation emanating from these stars is sculpting the nebula's wall by slowly eroding it away and giving this clear distinction in the image between the brown and the blue. As I mentioned, you can very clearly see the dense cloud of gas and dust and how they are forming the edge of the nebula. And dramatic pillars are rising above this glowing wall of gas, resisting the blistering UV radiation coming from the young stars. And on top of that, you are also seeing these light stream like things which rise from the celestial mountains. But these are actually hot and ionized gas and warm dust streaming away from the nebula due to the intense ultraviolet radiation that is impinging on them. In a whole, you can very clearly see a lot of stars are being formed from the dust inside this nebula. There are each dot that you see in this image is essentially a star very much like our own, and many of these stars could also be harboring planets. So in one sense, this is a magnificent picture stretching across 12 light years from end to end, as you can see. And there are bubbles and cavities which are being blown away by the intense radiation and the stellar winds of newborn stars, and there are signatures all throughout of them in this picture. There are also structures which and features in the image, as you can see pointed out, which people are still trying to understand. And there is also another very important feature which we are seeing here is the case that while the effect of the massive stars with their violent winds and high energy radiation is often apparent, we know very little about the influence of the more numerous low mass stars. And as they form, these stars create narrow opposing jets, as you can see, and which can inject a lot of momentum and energy into the clouds. This reduces the fraction of the nebula material that can seed further new stars, and therefore this is a tussle between things that enhance star formation and processes which suppress star formation. And this Carina Nebula image is a testimony to this fact that there is a very delicate balance between sparking star formation and stopping star formation, and which will give us a lot of information in the days to come. And the spectacular thing is that these were things which we had not seen with the Hubble, and it has been possible to see them through the JWST at present. So I hope that answers your question, Dipanshu, when you asked about the prominent images, features in this image. There was another question related to the fact that the HST's image exposure of the same field was about 2 weeks, but JWST was exposed for only about around 12 hours. But there is still so much difference in details of the two images, and why is that? So to answer your question, the main thing to note here, it is not as much about the exposure time, and as much it is about the size of the telescopes, where the JWST and the HS is beating the HST. The Webb has a 6.6 meter diameter primary mirror, as you can see in this image shown here. It is quite large, and for context, the Hubble's mirror is only around 2.4 meter in diameter. And the larger mirror size has allowed us or has allowed JWST to capture very high resolution images of the sky, and the mirror also needs to be stable at very cold temperatures, which is why it is made up of beryllium and coated with gold, as gold is among the best reflectors of infrared light. And in this primary JWST mirror, there are 18 hexagonal segments, as you can see, which give it which are so aligned to give a near circular shape. And the Webb's mirror are actually like these bucket that collects light, immediately send to its instrument. So the more infrared light that we can gather, the more we can learn about the universe. And with a mirror that is around 3 times wider, the JWST will also be able to see objects which are much fainter, typically about 8 to 10 times fainter than what Hubble saw, and allowing us to peer even further and further into space. And this has been a catch that has been seen in all the JWST images as compared to the HST image, and it also has a very large field of view. So these are some of the things which is allowing us primarily to get the resolution and disintegrate it and the image into such finer details. Hence, another thing that is worth mentioning in this regard is that the Hubble Space Telescope and the James Webb Telescope operate in different bands of the electromagnetic spectrum. The Hubble operates between 90 to 2000 nanometers, whereas in the optical, and whereas the James Webb Telescope operates is sensitive to light of wavelengths from 600 nanometers to 28,000 nanometers, operating primarily in the infrared. And the primary advantage that this gives us is that a complementary information. For example, as you can see over here on the left, there is a visible light image of some crocodiles and meerkats, whereas on the right we see an infrared light image of the same objects, and you can see the difference that is apparent. Although in the visible they appear somewhat similar, whereas you can see in the infrared light image the meerkats are glowing very radiantly compared to the crocodile, which is only faintly brighter than the ground. So this is another detail which distinguishes the JWST and the HSTs, that the JWST observes in the infrared bands. And why is this important? Because the stars and planets that are forming lie hidden behind cocoons of dust that absorb visible light. However, the infrared light emitted by these regions can penetrate through this dusty shroud and really reveal to us what is lying behind these dusty curtains. And therefore, the dust extinction in the case of optical light is very high, which is where Hubble operates. Whereas in the case of JWST, we are able to peer through dust and look through dust and see what is there, what we didn't see earlier. As you can see in this image, I'm showing in the Carina Nebula as seen by the Hubble and as seen by the JWST. You can right away see that there are the number of dots representing stars or galaxies is much more in the JWST image. And particularly if you focus on the bottom center, you will see that there are a number of stars which are being seen through this infrared through by JWST, which were not seen in Hubble. Hubble was not aware of the presence of these objects, which have revealed themselves very nicely in the JWST images. So this is the primary reason, the two reasons of the higher resolution due to the bigger mirror sizes and collecting areas, that we are able to get to see such intricate details of the Carina Nebula field. And secondly, of the fact that the infrared emission peers through the dust and allows us to see what is behind these dusty curtains, and unlike the optical emission, which is mostly absorbed. I hope that answers your question. Next, we will move on to another nebula, which was captured by the James Webb Telescope, which is the Southern Ring Nebula. In this regard, we received questions from Krishna and Kushi, which I will answer. So the question was that, as you can see in this image on the left and on the right, captured by JWST, the MIRCAM instrument in the near infrared, and the MIRI instrument in the mid infrared. And her question was, what are we seeing here? So what we are seeing here is essentially the Southern Ring Nebula, located some 2,500 light years away in the constellation of Vela. And this is a planetary nebula, unlike the earlier case, which was a star-forming nebula and a site of the birth of the stars. This is a nebula which we expect, as I had explained earlier, towards the end of the life of a star. The planetary nebula are the final stage in the lives of intermediate mass or low mass stars that evolve away from the main sequence and expand into the red giant phase. And this image, this scene, was created by a wide dwarf star, much like how our sun would become after it stopped burning fuel through nuclear fusion. These outer layers have come out, or have been ejected at the end of the lifetime of the star, and forming in the nebula and the glowing gas which you see here. In this NIRCAM image, the white dwarf is not visible, which creates this nebula. On contrary, we have its binary partner, which appears as here at the center, and which you can see in this image here. The partner, which is much brighter, but it has not undergone on its explosion, and will probably do so and participate in another planetary nebular event in the future. In the meantime, this brighter star at the center influences the nebula's appearance. However, as the two objects undergo a swirl and continue to orbit each other, they stir this pot of hot gas and dust that you see, causing asymmetrical patterns and shell. each shell represents an episode where the fainter invisible star in the NIRCam image lost some of its mass. The wider shells of gas towards the outer areas were ejected earlier, and the ones closer to the star were recent episodes of mass loss. And tracing these ejections would allow us to get an idea of the history of the evolution of this binary system. The NIRCam image also shows us on some spotlights and of light traveling through the holes in these nebular dusty ejections and shooting away, as you can see. But if you now compare and move to the mid-infrared image, we see that the dying star, which caused this entire nebula, is very clearly visible, the white dwarf star, and it is cloaked in thick layers of dust, and it appears much brighter, larger, and redder than it did at all in the NIRCam image. So this are some of the details which we are getting in regarding the last few moments in the life of a star when it undergoes when it shoots and ejects out its outer layers in the form of a nebula here. So there were particular questions asked regarding the Southern Ring Nebula as to where it is located. As I had mentioned, this is very bright and extremely studied planetary nebula located in the Vela constellation. And it is located typically around 2000 to 2500 light years from Earth. And the second question was about what is special about the Southern Ring Nebula and why is it important to study this nebula. In this respect, we have already seen that the Webb has been able to give us an unprecedented view of the dying star which created this nebula and brought to us exceptional structures present in the nebula, the shells, hills, and their crossings. And therefore, this will give us an idea as to how the stars are shaping the gas and dust around them towards the end of their lives when they are ejecting the outer layers. Yes, and it will also give us a peek into the late stages of a star's life and help us understand how the stars evolve and transform their environments around them. And as the star ejects these shells of materials, dust and molecules form within them, these ejected shells, and the elements contained within the ultimately formed planetary nebula, such as carbon, oxygen, and nitrogen, are recycled into the surrounding space, and these may be used for forming new stars and planets. And definitely the dust will eventually enrich the areas around the dying star and expanding into the interstellar medium. Therefore, we will get an understanding of how the dying stars spread atoms and molecules into the space and how that changes the chemistry of this of our universe. So these are some of the reasons why studying the Southern Ring Nebula is special, because it gives us an unprecedented view of the late ends of a star's life. So I've already answered the third question: how far is this nebula from Earth? It is around 2000 light years. The fourth question was how fast is the nebula expanding? So the gases are moving from the dying star at its center at a speed of around 9 miles per second. And the last question was, is the Southern Ring Nebula an emission nebula, and why do emission nebulas appear red? Yes, an emission nebula, it's an emission nebula. An emission nebula is essentially a nebula formed of ionized gases, which got ionized due to high energy radiation being emitted from the nearby hot dying star. And an important thing to note here that the nebula's colors would depend on its chemical composition and the degree of ionization, essentially. So therefore, due to the vast abundance and the prevalence of hydrogen in the interstellar gas and its relatively low energy of ionization, most emission nebulas in the optical would appear red due to the strong emissions of the Balmer lines, essentially the H alpha line. And if more energy is available, then other elements could get ionized, and that is the reason why we see these nebulas to appear red, right? Because of the abundance of the hydrogen in them. I hope that answers your question, and with that we will move on to the next portion of the program.
Thank you, Anirban. We have now so far looked at the extrasolar planet. We've looked at these two nebulae, right? And now the time comes when we move. We've also looked at these galaxies, but now the time comes to move to very large distances, to the very edge of the universe, to try and understand questions that JWST was designed to solve, which is what's happening when did the first stars form? Can we find the most distant galaxies? And in order to do that, they made an observation of a very distant cluster called SMACS 0723. And we have a few questions on that. So we'll begin with Rashi answering a question from Suresh Parekh from Gujarat, who's asked a question about this cluster and about the gravitational lensing that you can see in this cluster. So over to you, Rashi. Please share your screen and answer.
Hi, Yogi. Actually, I answered that question before. I cannot hear you.
Yogesh, you are mute.
Rashi, we can't hear you at all.
Hello.
Yeah, now it's there.
Yeah. So,
Your voice is
I
very
answered
low.
that question before. In the first part.
You've already answered that question. That's correct. So
Yeah.
we will move on now, and there is a question that was received, which is why are all the arcs red in color? And let me try to answer that. And that is because these are very distant galaxies. And I told you that distant galaxies are characterized by redshift, by having a high redshift. So what is happening here is that these galaxies are, the light, the optical light emitted by that galaxy is getting redshifted into the infrared and even into the mid-infrared. And because of that, what is happening is these particular galaxies are A1 extremely faint, but also extremely red in color because they're very distant. So in order to show you what I'm talking about, let me just share my screen and show you a very interesting site. It's called webcompare.com. We've discussed these galaxies. Okay. So let's try to zoom in. So what they've done at this website is that they have put both the Hubble image and the image of obtained of the same object obtained with JWST. Okay, so look at this particular object. Okay, focus your attention on this. This is a very bright arc of a galaxy which is located behind the cluster. So where is the cluster? I have to. So you have to focus your attention on this particular object. And now, if you see with Hubble, this particular object is extremely faint. You can barely see it because it is so red that Hubble is not able to detect the light from it. But the moment you go into the infrared, you are able to see the light very, very clearly. That galaxy appears very, very bright. So there are any number of arcs in this image. Let me just draw your attention to some of them. So there is a arc over here. There is an 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 arc over here. 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 Okay. So all of these, literally tens of arcs are there. If you zoom in even more, you'll see more arcs. There's an arc over here, and so on. And on the other hand, if you compare it with the Hubble image also shows some arcs, but as you can see, they are much fainter and much more difficult to detect. So this is the answer to the question, which is why are these arcs invariably red? The answer is they are extremely distant. So with that, we come to the end of the questions that we had received via our Google Forms.
Hi.
light years away, it is probably going to be the same more or less now. But if you take objects which are very far away, and the galaxies we are looking at are more than 13 billion light years away, and they are they're completely different. I mean, they could have changed completely. They may not exist. They may have merged with other galaxies. Everything. They don't exist the way they existed 13.1 billion years ago. And the reverse is also true. So if you take the descendants of that galaxy and see whether those people are observing us, no, they can't be, because that galaxy is very far away. So they will not be seeing us. They will be seeing the Milky Way as it was 13.1 billion years in the past, where it may not have even existed. So it really is a very, very confusing game here. And so it's very hard to tell. So we move on to the other questions. We heard that the JWST was hit by an asteroid and had some damage. This is a question from Ishara Vikramasinghe. From the name, I suppose this is from Sri Lanka. What is the status of the damage now? Was it repaired? Would it impact the images taken from JWST? So such kind of micrometeorite hits have been expected. They have been modeled. But the hit that occurred in late May was from a more energetic particle than was expected so quickly. So as you know, the less energetic, low mass micrometeorites are much more common in the solar system. And so a hit by one of them was expected. But this is a slightly bigger hit than what was expected. But the damage is not very severe. Remember, all the images that we have seen were taken mostly in the month of June last month, and they're nearly perfect. So it remains to be seen how much the impact long term will be, because if there has been one hit in May, there surely will be more hits in the future, and damage will accumulate. There is no possibility of any repair. Remember, this is 15 lakh kilometers away. So there is absolutely no chance of getting things fixed in any way. Using some software, one may be able to mitigate the effects on the images, maybe do some additional software processing to mitigate those effects, but not cure it completely. Narendra S is asking, I had a question, how are we determining the distance of the galaxy from the JWST image? As it said that the farthest galaxy seen is about 300 million years after the Big Bang. This is a very, very interesting question. So the way we determine distance is by measuring the redshift, which means suppose we have a line, let's say the H alpha line. We measure how much it has shifted to longer wavelengths. That gives us an unambiguous measurement of the redshift. It's a bit dangerous to measure only one line, so people try to measure multiple lines, so that if all lines give you a consistent redshift, that means you have identified the lines correctly and the redshift is robust. In the era of HST, this was quite difficult to do, but with JWST and its much more advanced spectrographs, we are able to find many, many more lines than one, and therefore you can get a robust redshift. Now, translating that redshift into a distance or a look back time and so on is based on the cosmological model and the parameters of the cosmological model that we are using. So right now, over the last 20, 30 years, what is known as the lambda CDM model of the universe has gained prominence due to a number of measurements and experiments that have been done to verify its correctness. So we believe broadly the lambda CDM model is correct, and the parameters like the Hubble constant and the dark energy parameters that we have measured, the cosmological constant, are reasonably accurate, and therefore with a reasonable degree of certainty we can say that the galaxy we are looking at is 13 billion years old or 13.3 billion years, and so on. Very interesting question. There is one more question from Kiran Mehta. Can some electromagnetic processes exist that would get redshifted to the range of wavelengths beyond the infrared, which we are ignoring? So absolutely. So for example, there could be dust emission from this distant galaxy in the far infrared, okay, say at a wavelength of 800 micron or 1000 micron and so on. Now, if this galaxy is at redshift 6, then that thing would get redshifted by a factor of 7 and go to wavelengths of, instead of 1000 micron, it will go to 7000 micron. And therefore, you begin to approach the boundary between far infrared and radio, and eventually you'll go into the high frequency radio and low frequency radio and so on. So everything gets redshifted. Every emission gets redshifted. It is not as if only optical gets redshifted and the infrared remains untouched. Everything gets redshifted by the exact amount, because this redshift is cosmological in nature. It's caused by the expansion of the universe. Yes, so I think we've reached the end of the questions. Can one of you check and confirm that there are no more questions that remain unanswered? Anirban or Rashi?
I think there is a question by Akash in which he has asked, he has asked that the condition of that place will be different from now because we are looking into the past or something like that. Have you answered that question?
Yeah. I think we did that, right? We said that if you are looking at a nebula which is 7,000 light years away, then
okay.
1,000 in the past.
Yeah. And okay, then.
Yeah. So Anirban, you said there are some 2-3 questions from Adita and Nikhil. If you're able to see them, can you just try to answer them?
Can you hear me?
I think this must have come in on the Google form.
I guess they lost. So just end the stream. Just say that, okay, bye, we'll meet again. Camera on करते. Rashi?
Recording in progress. And there are other questions also, Yogesh. What are the list of the celestial objects that JWST is planned to photograph? So
yeah, that is not an easy question to answer because it's a very long list. The program for the first 6 months has already been decided, and those observations of stars, nebulae, galaxies, quasars, the distant universe, gravitational lensing, all of that is being planned. The JWST puts out a weekly schedule so that you can see what they're going to observe in the next week. Whatever is going to be observed in the first 6 months or so is part of what is called early release science. And that data, normally with the JWST, data will be kept private to the proposers. There is a proprietary period of about a year. But for the ERS, that period has been waived. So the data will be made public immediately. So lots and lots of data is going to come out in the next 6 months.
Okay, she has also asked how accurate are the spectra taken by JWST?
They're very good because the spectrographs, both on NIRIS and NIRSPEC, are extremely high quality spectrographs. MIRI also has a spectrograph, and these three spectrographs together are able to give us a much better picture than what Hubble could. One main reason is that now at high redshifts, we are seeing the rest frame optical, which is getting redshifted into the infrared, and all the techniques and tools that have been developed in optical astronomy can be applied to high redshift JWST galaxies straight away. All the Balmer lines will be visible. Some of the metal lines will also be visible.
Because it's the higher sensitivity also, right? Because earlier we could not detect many of the lines.
But that may be counteracted by the larger distance. You are trying to see very faint galaxies at very high redshift. So yes, so it may, the signal to noise may not be that great, but because you are able to see a fairly rich part of the spectrum, it's quite interesting. And in the nearby universe also, detecting water vapor is going to become very easy.
Hello.
There are a couple, there are two more questions. How much time will it take to photograph a galaxy cluster more than 5 billion light years away by JWST? And yeah, can you answer that question? Hello. Yeah, I think we should end it here. Yeah. Yeah, and this video will be put up on the YouTube channel, so you can access it later as well.
Yeah, and our sincere apologies for the frequent loss of network and for the glitch at the beginning. We were delayed in starting by nearly 20 minutes. My sincere apologies. But as Rashi has said, we are going to edit all these videos and every specific question can be then answered. And we'll have little clips of 4 or 5 minutes long, which will answer all the questions that we've received. So thanks to all of you who have joined us live today, and to those of you who have sent in some very interesting questions. We hope that in the future, there are many more opportunities like this for us to go forth and answer questions from the public. Thank you very much. Now we will close this program.